Welcome to this video for Material Science 410. We'll be discussing some of the details behind the silicone elastomer lab. We'll start with getting to know how we fabricate our master for the molding of a silicone by way of hydrosilylation over top of that master. We take advantage of the reverse fabrication, if you want, of a compact disc. So a CDR, a writable CD, is shown here, and you can see that a small portion has been cut away from the compact disc. This would be what students would use to access their master, is some of that cutaway compact disc. In cross-section, the compact disc consists of a thick polycarbonate base, a thin aluminum layer, and a small overcasting of acrylic over top, which includes the label. So in cross-section, sort of zoomed in further, we'll see that there is topography present in that structure. So again, polycarbonate base, aluminum as the next layer, and the acrylic at the top. And we now see that there is some topographic information buried within this sandwich structure. So if we could remove one portion of that, peel the structure apart, we might be able to access a master for a PDMS. Okay, and so that is what's done is high-tack tape is applied to the top of the compact disc. So this would be where the label would be. And after allowing adhesion of that high-tack tape to the top, you can simply peel that away from a freshly cut portion of a compact disc and remove the acrylic, which is now upside down, from the polycarbonate. So we see that acrylic kind of shown here. And clearly the aluminum is the next part. Great. Okay, so it is the acrylic aluminum that will be our master, and by pouring a mixture of polyhydrosiloxane with polyvinyl siloxane and catalyst over top of that, we have the ability to set by Cure reaction of hydrosilylation and driven at about 80 degrees C to cross-link that PDMS in place and allow for molding and inheritance of the topography of that aluminum master that we see above. So after removal of the acrylic aluminum layer, we'll end up with a molded PDMS that is available for investigation. So as part of a goal, we'll use the compact disc to mold and make replicates by way of PDMS hydrosilylation chemistry. And our goal is to determine how well the original features in the aluminum layer are copied to the silicone elastomer. So if this is our molded PDMS, a really good comparison might be to the polycarbonate, because it once rested over top of the acrylic aluminum layer in the exact same fashion. So if our PDMS is, in fact, behaves as a twin to the polycarbonate, then we know we've got a good duplication of the features. And as we mentioned in a previous video, the topography here in the PDMS is sort of the opposite of that of the acrylic and aluminum topography found by removal of that layer from the polycarbonate. Okay, so to sort of put bullets to everything we've said there, we have here cross-linking reaction by hydrosilylation will covalently bond all polymer molecules together set the PDMS from a liquid portion into now more of a elastomeric portion due to cross-linking, and that new silicone will behave as an elastomer, therefore, due to those covalent linkages by hydrosylation, and will allow shape retention and inheritance of the structure. That should be equivalent to the polycarbonate. So to investigate structures, we'll be using atomic force microscopy, a technique that uses a stylus to study the vertical dimensions across a plane of interest in the XY dimensions to understand height and ultimately pattern such as pitch and wavelength and amplitude, if you will, for a pattern of features in a compact disc. An AFM image is shown here, and so again, we know that a compact disc has parallel tracks of information all the way around the compact disc. And at a level of 10 microns by 10 microns, the circularity of those tracks is not obvious. And so they do, in fact, look like parallel trenches with parallel crests around the area. So an image that is about 10 microns by 10 microns is an appropriate scan size to show 6 to 7 repeats of the pattern that we see in the compact disc. We can also use laser diffraction to study how the Fraunhofer equation can predict the periodicity of our diffraction grating as we impose lasers of different wavelength, blue, green, and red lasers, onto our materials for diffraction and study that way. And lastly, we can use XPS to determine the elemental composition of the PDMS mold and to try to determine if there's residual catalyst left over in the elastomer and possibly identify the metal present in that catalyst. So as a brief summary here of what you'll see, and you'll get more details from your instructor and on Canvas, your lab report for this experiment will be written individually in a technical memo format, and you will report on some of these themes that we've just touched on in this video. Thank you for joining us.